To start. So, welcome everyone to this edition of Verifiability Talk. I'm really glad to see many of you here, despite the Easter holidays approaching and also school holidays. So, it's my honor to introduce today's speaker, Alice Miller. I was telling Alice before you joined that I was enjoying many of her pieces of work when right after my PhD, when she was doing symmetry reduction stuff, which was amazing contributions to the field of model checking. She has been contributing to the field of formal methods verification ever since. And she'll be talking about another piece of exciting work, which is about real-time overtaking using model checking. Thank you very much, Alice, for having accepted our invitation. Before we move to the talk, this talk is being recorded and will be posted on YouTube. So if you don't want your name to appear, you could join us as a guest. Thank you very much again, Alice, and the floor is yours.
Hi, thanks very much. Thank you very much for inviting me, everybody. The talk I'm going to give, it's very heavily based on a talk I gave last year at Formal Method for Autonomous Systems. So I apologise if you're at that talk as well, but I've kind of updated it a bit at the end because with the stuff that I've done more recently. So hopefully everybody can see my slides. So this is the general slide. It involves lots of people, so I'll introduce the other people as I go along. So it's the sort of progress that I've made in towards doing real-time overtaking planning using model checking. Okay, so here's an outline of the talk. So the first part of the talk is basically what I did last year and presented at FMAS. And the second part, which is actually only a few slides and a few pictures, so by the time we get to that point, you can relax. That's just an update on the current work where we're moving the approach to robots to try and get closer to actually applying this sort of stuff to physical systems. Okay, so that I'm part of the governance and regulation node in the TAS grants. There's several other people who are here. I can see that Andrew's here. He's also part of that as well. And this does very much link in with what we're doing there, but I didn't have time really at the end of the talk to make the connection, which is what I had planned to do. So this first bit of work, which is the overtaking work with model checking, this involves, this was a master's student, Domantis, was doing the implementation of this. And it's part of a long-time collaboration between myself and Bernd Paul. And Bernd is in our engineering department here at Glasgow, and I've worked with him for many years. And also Ivaylo, who's also here just now, Ivaylo Valkov, he's my PhD student, and he was involved in this work as well. So as an outline of the part one of the talk, I'm going to talk about what the approach actually is, and there's going to be a very short video, which I warn you now hasn't got any sound, in case you're wondering that I haven't connected the sound up. A little bit of an introduction about Promula and spin. I know lots of people here have done model checking, and quite a lot of people sneer a little bit about Promula and spin because it's much more basic than other model checkers, but I definitely always often come back to Promula and spin because it's a very good way of just sort of representing communication within a system. I know that Andrew Ireland, who's also here, is also a big fan of spin. Then I'm going to introduce the system and loosely describe the Promula model, and I'm not giving any detail. And then I'm going to give a few slides about the Unity games engine, which we use to do our simulation, and then describe how we combine these two things together, and then talk about the results and the conclusion from this part of the work, which has led to the second part of the talk and what we thought we should do next. So this slide will come up repeatedly throughout this talk, because this summarizes what our approach is. On the left, we have our Unity simulation of a car, and the car we're interested in this diagram is the green car, which is doing the overtaking, and it has cars in front of it and cars coming towards it. And what are we going to do is we got sensor readings coming from the car telling us the positions of the other cars in the system, and other things as well, like speeds, etc. And those sensor readings are fed into our Promula model. We start off with the Promula template, which is expecting these things in order to be able to initialize our model, and then that allows us to create a Promula specification, which we combine with our LTL property, do a little bit of spin magic, and it will come back with some instructions as to how to do a safe overtake if it's possible. So here's the video. Hopefully I can get this to work. As I say, there's no sound. It's a couple of minutes long, but once we've done a few things, I'll just terminate it. That's a car just peeking out into the lane just to see what's coming. And it now decides it can't overtake because the car's coming too close. It's a bit jittery, this video. I'll just wait until it manages to do a successful overtake. So therefore, there it's successfully managed to overtake. And sometimes it might have two cars in front of it, and it might try and overtake both of them at once. So I'll stop the video now, because I think you get the idea. Okay, it's a little reminder about Promula and spin. I expect several people here teach Promula and spin, so they're very aware of it. But just as a reminder, if you're used to using a different model check, it will just get you back into the way of thinking of it. So it's a tool for analyzing Promula programs, and it allows you to do that via simulation. And there are three types of simulation you can do, either random, interactive, or guided. And we're particularly interested in the guided simulation in this talk. So random just means go and show me what you can do, and it will run a particular execution. Interactive is when you try and guide the simulation, you try and force it to go a particular way. And a guided one is one which is led by a particular execution trace which you may have generated via a verification. And that's exactly what we're going to do here. So that's simulation. And verification, which is what we normally use spin for, is when we have a program and we have a logical property, for example, and we just want to check whether our property holds. And it will just go off and search the entire state space until it see if it comes up with a contradiction to the property. And that's what we mean when we're talking about using spin for verification. But actually, really, we're mainly going to be using it for simulation in this case. It's verification and simulation, in fact. We're going to do a verification to come up with a simulation, which is going to be useful. So I'm not going to show you any Promula in this talk, but just a summary of what you can do with Promula programs. Again, I find it very useful when you're building a system and you've got messages going around your system and you just want to check that things are happening in the right order, or they don't deadlock, for example. Although, in fact, in this example, there isn't any message passing going on, but you can have message passing between processes. You've got your usual variables, etc. And you have channels along which you can send messages. As I say, our models are very simple. We've only consisted of a single process, which is the autonomous car itself. And we also have a process which represents our linear time temporal logic property. The main feature that we exploit in this model is just simple non-determinism. We give the system a lot of choices, and it decides which choice is going to make at any point. And we want to find how that non-determinism is broken in order to solve our problem, which is the overtaking. So this non-determinism allows our autonomous vehicle to make its own decisions. So generally with model checking, and in particular with spin, what we do is we have a model and an LTL property, and we want to show that our model satisfies the property. So we have our Promula model, which is in the pink ellipse on the side, and we have our LTL property, and I'll give you some examples of those in a minute, which is converted into another spin process, which is called a never claim. And they're all munged together and given to spin, and it will give us a result to tell us whether the property is true or not. So coming to our overtaking system, this is what the abstraction of the overtaking system that we are referring to. So our Promula program is assuming we have a system like this, and this matches onto our Unity simulation as well. So just so you can be familiar with the terms, we have the autonomous vehicle, which is the one at the bottom left, which is currently travelling in the left lane, and we refer to that as AV. We have other vehicles which are moving in the same direction in front of us, and they're referred to as FV. And in this diagram, we just got two of them, FV1 and FV2. And in this diagram, we also have an oncoming vehicle, OV. Now, we could have more vehicles in our system, depending on what the simulated vehicle has spotted coming up in the distance. So when we look at the Unity, we'll be able to see that it can actually see quite a long way in the distance. We make other assumptions, and I'll introduce them as we go on. And in fact, the way we model it, we assume that the autonomous vehicle is actually standing still and the other vehicles are moving towards and away from it. That's just the way we model it to make it easier to model. And our vehicle, basically our Promula model is just a mapping of this state machine into Promula. So we start off at the bottom of this diagram at state main 1, and we attempt to move forward. We then do a check to see whether we've crashed. Now, it would be very unfortunate if it crashed right at the beginning, but we're going to end up coming back to this state after we've made a decision. So we always check to see whether we've crashed, and if not, then we check to see whether we have already done an overtake. And if we haven't, if we have, then we say, yes, okay, that's true. So we go back to finish. Otherwise, we choose an action to take, which could be move to the left lane. And we only do that if we're not already in the left lane. So we check to see the left lane's false. Or we could move to the right lane, which is the one on the far right-hand side, accelerate, drive, or brake. And I'll explain what happens in more detail about these actions in the next couple of slides. And then we check again to see whether we've crashed. And if we have, then we just finish and we set our flag to be true. Otherwise, we come back round again and we do the whole thing again. So this is having assumed that we set up our Promula model from our simulation, and we keep going until we get to the point where we finish. So at that point, we've either crashed or we've overtaken. We just have to hope that we've overtaken. So what these actions are actually doing, a left lane chain just means move into the left lane and move forward one position per time step. If we accelerate, then we're just moving straight forward and we're moving 2 positions per time step. Driving, we're just moving forward. Braking, we move at half the speed. So we don't actually come to a stop. We just slow down if we brake. And similarly for right lane change. And then we just have these conditions, which is left lane is equal to true or false, would depend on whether the autonomous vehicle was in the left lane or not. Crashed is equal to true if the AV has crashed into the oncoming vehicle or one of the forward vehicles, and overtake complete is equal to true. Now, overtake complete is equal to true is the proposition of interest. That's what we're trying to do, is get to a state where that's true. So if we can see how the autonomous vehicle moves by these examples here. So the left-hand example here is where we start off. Now you notice that the AV is not actually moving forward, it's staying in the same horizontal position. That's because we found it easier just to model the other vehicles coming towards it. It might move into the right-hand lane and back into the left-hand lane, but it's not actually moving. So if we look at the first example, if the if the AV is accelerating, it's going to move forward within one time step, it's going to move forward 2 spaces, whereas the forward vehicle is actually only moving 1 space forward. So in fact, we gain 1 position on the forward vehicle in front of it. That's why the forward vehicle seems to come towards it. The oncoming vehicle would have been moving 1 space forward, but because we've moved 2 spaces towards it, it's now moved down 3 spaces. If we look at the right hand, the third one, where we're just moving into the right hand lane, everybody else is still moving while we're moving into the right hand lane. So the distances are staying the same. We're moving into the right hand lane and moving forward 1. The forward vehicle is also moving forward 1, so its distance from us is not changing. The oncoming vehicle is moving forward 1 at the same time as we're moving forward 1, so it appears to move forward 2 spaces, etc. That's just the way we model it, but it's not really that relevant to this talk. So going back to our original diagram of what we're doing in our whole system. So we talked a little bit about we're going to start looking at it in detail. So let's have a look at the Promula specification. Now the Promula specification, I've taken out the slides which had the Promula in this talk because I just felt that was too detailed and wouldn't give me time to move on. But we create that specification from that original state machine that we started off with. So we have to attach an LTL property. So just a quick revision about how LTL is expressed. Now, one thing that's important to remember is that all LTL properties apply to every path in the system. So there's an implicit for every path in front of every property. So we don't have to put for every path because it's got to be true for every path. So I've just got a couple of examples here. So the square brackets mean in every state. So square brackets P means for every path in every state P is true. So basically, universally P is true. The angle brackets means eventually. So angle bracket P means in every path eventually P is true. Now what we can't say in spin, in LTL rather, we can't say there is some, we can't explicitly say there is some path for which something is true. We can't do existential properties. However, we can get round that with spin by saying that the negation of the property is true in every path. And then if it finds a path in which that's not true, it will essentially have found a path for which the property itself is true. So if we have a property which says it's always true that not R is true, so in every path, in every state, not R is true, and we run that property and find there's a violation of that, it must be the case that there is some path at which R is true in some state. So we found a counterexample, and that's what we use when we're actually trying to prove an existential property in spin, even though you can't express that in LTL, but it's a very useful little trick to know with spin. So our property, we're going to say it's never true. So in all paths, it's not true that a successful overtake has occurred. And what we're actually looking for is an error path to that property. If spin identifies a path in which that property is not true, it has identified a path in which a successful overtake has occurred. So when we run our Promula model with spin, using the property that it's never true that an overtake can occur, when spin finds a violating path, so a property in which an overtake has occurred, it will store that path. And then we can run a guided simulation which uses that path that it's stored in order to investigate what happened in order to lead to that error or to a successful overtake in our case. If we annotate our Promula code with print statements, we can actually get out the actions that we took or the decisions we made with that non-determinism in order to make that successful overtake. So this is how we managed to extract the list of actions that we have to take in order to create to execute that successful overtake. So if we go back to the green car again, we sent off our sensor readings to update the Promula model. We've used our LTL property, which says it's not true, it's not possible to ever do a successful overtake. We've given it to Spin. Spin has found that's not true. It's found a violating execution, and it can regurgitate that execution by and we can extract the actions that we had to take in order to do that overtake, and we give that back to the Unity simulator, gives the instructions to the little green car, and the green car will execute that overtake without crashing into the car. Obviously, if it's not possible to do an overtake, it won't send back a set of actions to do an overtake. So our model was quite coarse. Obviously, we've discretized the space, and it can lead to some unsafe behavior, which we noticed 2 scenarios which were not captured in our model. First of all, in order to judge what is a safe distance, we had to put a danger zone around our oncoming vehicle just to make sure that we gave it plenty of space to get past. And this meant that we missed some opportunities to overtake because we were being overcautious. Also, if you imagine you're in the situation that we have at the bottom here, and you believe that you can't get back into your lane, but by not getting back into your lane, you're actually going to crash into the vehicle coming. You actually want to throw caution to the wind and try and get back into your lane. It's the safest option to take. So in that case, we revert to a different model, which removes the danger zone in order to get us back into lane. Another scenario, which isn't to do with the safety zone, is to do with the fact that if we've trying to overtake 2 vehicles, we might overtake 1 vehicle and not realize we've got to accelerate to get past the second one. And that's described in the paper. So sometimes we revert to a different model when we are in one of these 2 scenarios. So I'm going to have a little look at Unity now. So Unity is a games engine, and you can download various different things from it, install it, so you don't have to create them all yourself, you just plug them together. We took our vehicle model from the Unity Assets Store. It runs using the Unity physics engine, so unlike ours, it's actually using an actual physics engine. We can control the car by adjusting things like the throttle and the brake, etc. We just adjust the inputs into the games engine. Now, the maximum speed of the autonomous vehicle is 24.2 kilometers per hour, which seems very slow, but everything is reduced down in this model. So the distances and everything are much smaller, etc. So really, we're just sort of changing the granularity of everything. So it's not as unrealistic as it looks. If we're in accelerate mode, we can go up to 50.4 kilometers an hour. And if we're in the brake state, in the Unity engine, you can only go up to 7 kilometers an hour. So we've roughly mapped this onto our Promula model. The road is divided into 21-meter segments, and every maneuver takes about 3 seconds in the simulator driving at normal speed. So what we've had to do, we had to take all these measurements in the Unity engine and map them onto our units that we were using in our Promula model. So here's a view from the simulator. Each of the autonomous vehicle has got a 360-degree sensor with 100-meter range rather for sensing the left-hand vehicles. So they're the ones in front of it. It's got a front range sensor, which has got a 357-meter range. So you see the little car in the blue, that can be sensed by this sensor by the car, so it can see a long way in front of it. Okay, and what we can actually see from the sensors is shown by the boxes in that picture. Okay, so when we put the things together, the actual verification, when we've got a Promula model that we want to verify because we've given it more information, only takes about 20 milliseconds, which is pretty good. However, those of you who know how SPIN works, in order to compile that Promula model down to C, it takes about 3 seconds, which is massive. It's a massive sort of penalty to pay when the verification itself is so quick, because we've got a very small model. So in order to get the thing to work, we have to do a pause to generate our solution path. So it's not the fault of the verification, it's the fault of the compilation of the Promula model. So when I showed that video, the pauses were removed, but not particularly smoothly in some cases. Now, obviously, it would be very expensive to just keep recomputing the trajectory all the time. So we only do it when we've got new information that we need to take into account. Now, if no actions are returned by the verifier, then it just means that there isn't a successful overtake possible. So just stay in your lane. So these are what the results were. I'll discuss these on the next slide to just put them into context. Now, none of these errors that occurred, where there were 12 errors, we ran this for 3 hours, and so most of the time there was not errors. So we did a lot of distance and a lot of run time, and only had to do 12 runs in order to get that distance. So it's not that we didn't do very many runs, it's the fact that each run took a long time to actually get to an error. And most of the time the error was caused by, in this particular scenario, they're all caused by sensor failures with the Unity sensors. So, for example, it thought that there was a car in the left-hand lane when there wasn't, or vice versa, so it caused it to crash. So putting it into context, the total running time is over 31 hours, and we only crashed 12 times in that time. But in that time, we did 2,672 successful overtakes, because we forced the car to overtake whenever it was possible in order to get as much out of our model as possible. So it's unrealistic. You wouldn't normally do 5 overtakes per kilometre. The median distance it took before it crashed was about 40.6 kilometres. So which doesn't seem that big, apart from the fact that we're forcing the car to overtake whenever it possibly can. We haven't included the pausing time in those times that we had on the previous slide. All of the errors were caused by the sensors or steering failures, so it wasn't down to the verifier producing an incorrect path. And as I said, we forced the vehicle to overtake as much as it possibly could. So in conclusion to that first part of the talk, what did we learn from doing these initial experiments? It was only a proof of concept, just to see whether we could get something up and running and get it all linked together. It worked pretty well, apart from that compilation time. So the limitations of this was the road segment size of 21 meters. It's too coarse if we're in a congested location. For example, in an urban situation. Obviously, if we had a finer resolution, we'd explode our state space, which isn't ideal. The predictability of the other road users is unrealistic. We're assuming that all the other traffic moves at a constant speed. We could try and put a little bit of unpredictability or uncertainty into this. We're already investigating using Prism to do a similar thing. As I said, the pausing of the simulation is the biggest problem with it, and we'll address that in future work, which is what we're hoping to do with the robots that I'm talking about in a minute. The Unity sensors are unreliable because they caused all the errors, but of course that's probably true in real life, that sensors are unreliable, so we can't just ignore that. We have to somehow learn to deal with that and to address that problem. So that's where we were. And in order to sort of address some of these limitations, we have taken the work a little bit further. So this new work is being done again by myself and Bernd, but also we have 2 PhD students working in the lab, and that's Christopher Chandler, who's the one on the left, and Julia Lafrata, who's on the right. And they both have built these robots in order for us to try and put one of the things we're trying to do is put the model checking on the robot. So it would have to be a far simplified model checking algorithm, just a little state machine working on the onboard Raspberry Pi. So this is Christopher's robot. It's a 2-wheel autonomous robot using a 360-degree 2D LiDAR and Raspberry Pi, and Julia's has got the same technology as that on it, and his version is adapted from the AlphaBot, which he's taken some things off. He's stripped it down to make it as simple as possible. And the Raspberry Pi is sitting on there, and that's where we want to put our actual little model checker. Obviously, we're going to be very limited in the amount of stuff we can put on there. And this is Julia's robot, which was it's based on Meccano, the chassis. She's also taken lots of stuff off it. It was interesting that I asked them both to give me a sentence about their robot, and Chris, who's the computer scientist, gave me a very sort of simple. I did ask them to send me a simple sentence as well, but she put much more sort of engineering detail in her description of her robot. That's what they look like. Now, I spent a long time on this diagram preparing it for this talk. This is what we're actually doing. So we've got two parts of this project which will be linked in together. So up the top we have Julia and Bernd with Julia's robot. What they're doing is they're linking that up again to a games engine, but in this case it's the Box2D games, which is a 2D physics engine for games. What the games engine is doing is it's receiving sensor information from the robot. It's fast forwarding to see what's coming up in the future based on its own idea of the world, and then it's sending back instructions like, for example, turn left because you're about to bump into that wall. On the bottom we have Chris's robot, and both of these robots, they're now moving around and receiving instructions, but we haven't got anywhere near as far as doing this, by the way. This is the plan. This is what we're doing. Julia's robot, I think, has linked up to the Box2D. So Chris's robot at the bottom, we're using model checking. This is the aim here, to do something similar to what we've done with the overtaking. Again, we're going to be sending the LiDAR and sensor information to our model checker, which is sitting on top of the robot itself. Very simple model checker. The model that it's based on is going to start off a very, very simple model. So not only are we going to be receiving information to give us instructions back, but we're going to be updating the model as we learn more about the world that we're in. So it's quite ambitious, but we feel like this is the next step forward from the overtaking model, to just try and make it something that's a bit more practical towards actual real-time overtaking. So I think that's the end of my slides, actually. Oh yeah, so we've also got a group of engineering master's students who are doing something similar, but they're actually using an actual planner in order so that we'll ultimately be able to compare the use of the model checker as a planner and an actual planner on the robot. Okay, so that's me.
Okay, thank you very much for this very interesting talk. We have ample time for discussion now, so are there any questions from the audience? Anyone wants to ask the first question? Andrew, please.
Alice, thanks so much for an interesting talk.
Thanks, Andrew.
So my question is kind of slightly hypothetical. So imagine you're on a country road, so going back to the cars, and it's a single track and there's passing places, and instead of having one car controlled by the model checker, you have two. Would they just, do you think they just get to a situation where they would kind of deadlock and wait for each other? Or do you think What do you think might happen?
I see. So yeah, we've got two autonomous cars coming towards each other. Yes, I mean, I've got no idea. As I say, that our model is very, very simple, and the assumptions we make are very straightforward, and we're only looking at it from one car's perspective. But I guess there would have to be some sort of protocol, wouldn't there? You'd have the rules of the road embedded in the software as well, wouldn't you?
But that's what happens in reality in Scottish roads in the west of Scotland. When you do get these competing
You picked the worst scenario, haven't you? Single lane traffic, two autonomous cars. What could possibly go wrong?
So your second project sounds really interesting, because the kind of idea of you've got a process model and then you've got the real world of the robot coming up against the wall or something, and you've got to adjust your process model, because many accidents happen because the real world and the process model get out of sync. So if you could bring them back into sync, that would be really neat.
Yeah, that's the idea. I mean, I think it's a way off, but that's what we're hoping to do. Yeah.
Thanks.
Thanks.
Thank you very much, Andrew. Are there any further questions? I could ask one until the next question arrives. So I think you're recalculating the plan over and over by sending queries to the model checker. Is there an idea to kind of synthesize some sort of plan that is improved over time? Do you see what I mean? Because I think you're encountering the same situation many times.
Oh yeah, definitely. I mean, but that's kind of that's a result of being in a very, very constrained environment, isn't it, with our simulator? So in our particular example, that's definitely true. There can only be a finite number of situations that you're in, but the idea was really just to show that as a proof of concept, you could do this. You could generate the plan automatically, and on when required.
I see Jan has turned his video on. Do you want to ask a question? Yeah, synthesis.
Yeah, it's again about the synthesis related to that, because we have a synthesis environment, and I mean what you're doing. There is this GR1 generalized reactivity, where you basically can have globally finally constraints. So you would have like globally finally succeed overtaking, and we had some people already use that on Raspberry Pis. And yeah, maybe that's something. The only issue with applying this would be that you would need some kind of assumptions that you add to your specification to make sure that this globally finally overtake is possible, right? So I'm not sure whether this is possible in your case to add these assumptions, like to find valid assumptions that would not be violated by an environment. Do you think something like that would be possible to formulate?
So the first thing you mentioned was that it is possible to overtake finally. I mean, in our situation, we were assuming that there are situations where it's not safe to overtake. So I guess, you know, when the oncoming vehicle's gone past, you then reassess to see whether it is possible to do an overtake, and then it's sort of a staged thing. So if it's not possible to overtake, you don't try, you wait, and then you try again later on.
But you would have the assumption that eventually later on there will be an opportunity, or because
I don't think. Yeah, I mean, in our model, I don't think that is assumed. I mean, it could be possible that the simulator could just give you an enormous, great big continuous stream of traffic, because actually what the car's doing is going around in a track, even though it's not obvious from the video. So if that right hand lane was completely full of a jam of traffic, it wouldn't be possible to overtake, because you'd never get to a point where it was possible to overtake. But it could keep checking. It could keep saying, okay, there's someone coming at this distance away from me. Is it possible? And the answer is no.
And this more, let's say, the more efficient implementation that you were talking about, would this be simply creating let's say, the game graph and solving reachability on it? Because it looks like that's the main problem you're interested. It's all safety problems and then just the reachability part. So is this something that you're looking at, or? when you said like take parts of the model checking algorithms?
Oh yes, yes. So exactly, yes. So it's actually quite cheap to check for safety properties, isn't it? So yes, we would just be, if we were just checking for safety properties, we wouldn't need all the automata stuff on top of our model checker. We could all actually do sort of the type of model checker where you don't actually keep all the states. You're just constantly sort of just doing I'm trying to think of the word for it, but I can't remember it. You're doing verification, but you're not storing the states like you would have to if you were doing something like
on the fly.
What's that? Sorry.
On the fly, I said.
Yeah, well, yeah, sort of on the fly, like liveness checking. You'd have to keep. I'm thinking of Patrice Godefroy and what he used to do, and I can't remember what the term is that.
Partial reduction, or.
No, it was his way of verification where you only do a particular type of verification because you're not keeping all your states. Therefore, it's much cheaper, obviously. So you just but I can't remember. I'd have to Google it. Probably a bit rude for me to Google when I'm the speaker. So yeah.
Okay. Yeah, I think the idea is clear. Although the name.
Mm-hmm. Yeah. I'm kicking myself. I'll get it straight away when I stop.
Good. Any other questions from the audience? Anyone else? The audience. If there are no further, and I was also thinking how much adding. So you have this acceleration and deceleration as discrete actions. Did you find any? So you said that there were a couple of cases that it was unsafe. Was it because of the discretization? Do you think adding more details about the dynamics and kinematics of the vehicle would make the model more useful, more precise, avoid more accidents?
It would. It definitely would make it more precise, but at the cost of intractability. And what we're trying to do, the reason why we're using model checking rather than something like neural networks or something, is we're trying to do something where it just has a definite decision. Do something at this point, don't do something at this point. So the good thing about model checking, it gives you a definite set of instructions rather than, well, if you're doing something with a continuous variables, for example, you're constantly moving towards something, but you're never actually there, are you? So it's just to say definitely make a decision rather than have this sort of vague, yes, it's probably okay to make that decision. This is why Bernd, who's not from a model checking world, is very attracted to model checking. He always has been. So because he comes from this very sort of continuous world and he really likes the finiteness of it.
Thank you very much. I don't see any further questions. So yeah, there is. Kirsten, please go ahead.
Hi, Kirsten.
Hi guys. Sorry, new laptop. Camera not working.
I was going to say nice to see you, Kirsten, but
yeah,
I can't.
Sorry, I've just only worked out that the camera isn't working, so another I have to complain about. But yeah, it's really interesting, the talk. Thank you very much. I've got a couple of questions. One is the simulation with Unity as a game engine. Did you find that if you run what looks like the same test, there is variation in the outcome? What I'm after is repeatability.
Yeah, so in terms of you mean in terms of simulation or in terms of the verification?
In terms of the simulation, because what you're doing is essentially model-based test generation, right?
Mm-hmm. So yeah, so it's variable. I mean, you get clumps of cars, for example, and sometimes there's a big space where there aren't any cars. So it's not, there is variability in the scenario that you've got. I mean, it was Demantis who did all the actual simulation stuff. So, and unfortunately he's not here, so he would be able to answer that a bit better about what actually happens with the game engine. It was variable enough for us to what, you know, as I said, the idea was just to get everything linked up together and actually to prove that it was a feasible concept to do it, so that obviously we're not going to do it with real physical things when we first try the ideas out. We're going to do it with a simulation, so the simulation is not going to be as variable as a physical system possibly would be.
Yeah, the reason I'm asking is we did a similar thing, and we used the Unreal Engine, or
right.
We used Scala as the simulator, and
yes, yeah,
underneath that with the physics. And what we found is when we run what looks like the same test, that the outcome can be different. So you don't get repeatability for various reasons. And we investigated this and developed a method to assess how much variability you get, because when you get this variability in a simulation, you know, in a digital simulation where you should be able to get the same result if you wanted to, for the purpose of debugging, for instance, right? You want, if something crashes, you want to look at it over and over again to see what happens and whether you fixed it properly. And so when you get these variations, it would be pretty useful to know whether that is a consequence of the way the system is, or whether this is a consequence of how the computation is run.
Yeah. I mean, I think Scala's a lot more sophisticated, isn't it, than the simulations we were running.
Yeah. So what we found is there is non-determinism in the system, especially in the physics engine. And anyone who develops these simulations should be well aware of the fact that they should expose any sources of non-determinism to the end user, so that you can control it if you so wish. So that goes quite far down, up to the operating system and the multi-threading in the hardware. But you need to be able to do that in order to get repeatable results, which I think is very important for digital twins and all sorts of things, which we rely on to make decisions. So that's just an observation. How of this you experienced.
I mean, I guess you know, the unreliability that we found with the sensors, etc., in the Unity model, I guess that's probably not consistent.
Yeah, and you know, I buy it that there is a level of non-determinism there in these sensors, to reflect reality. But if you have a simulated sensor, as the end user of such simulated sensor, I would like to be able to control that. Exactly for the reason that if there is a bug, then I want to be able to track it down, and not that will happen in the next 100 hours of simulation, perhaps, or not.
Yeah, sure. Good point.
It's really important that these, especially as we're embarking in these digital twins, that we expect all sorts of randomness and user for all sorts of good reasons, right? Because computers should be deterministic, or we know how to make them deterministic. We just sometimes are not diligent enough to spot the opportunities. And the other thing was, it's just an observation as well, is that we've done something very similar, although not from a verification point of view. We're developing assertions from the UK Highway Code, and we actually took an overtaking scenario into pieces to develop assertions which we're running over real simulation runs. So we look at the positions of everything that moves in Scala, put that into an SQL database, and then we've got highway code motivated SQL queries that identify where an overtaking scenario was okay. So obeyed the rules with, you know, sufficient space in front of you and that sort of thing, and where it was a near miss, and where there's a crash. Yeah, that is interesting to look at that.
Yes, definitely.
See where this overlaps, this work. So we've got a first draft on archive at the moment, but the paper's still worked on.
Okay, well, I look forward to seeing that then.
Yeah, I'm very happy to send it over.
Okay, great.
Thank you.
Thanks.
Thank you very much, Kirsten. There is a further question by Jan, I see. Or this is an old hand, I don't know.
No, it's a new question. So I was wondering, you are doing an abstraction to do the model checking, right? And you said that some of the crashes, they happened because of sensor errors. But I wonder, was there any case where, let's say, the abstraction was at fault to create plans that are not really feasible, or that leads
No,
to
that didn't happen in our case. We only had those two scenarios where it's because the discretization of the Unity engine, etc., maps very closely over to ours. I mean that it was possible to do that abstraction and it to be pretty true. So, but there were those two dodgy scenarios where we had to quickly jump over to another model in order to get it to work. So you probably don't really want to do that in real life, or unless you actually want to have a suite of models and you can flick between them.
Oh, okay. I mean, that's that's also quite interesting. So you are basically trying to kind of make the two abstractions of the real world very close, the one you use for model checking and the one for simulation. Okay.
Yeah.
Thank you.
Good. Are there any? Andrew, you have another question.
Hi, I was just picking up on the last point. It seems quite realistic to have different models. So your main model would be quite relaxed in the way you drive. But if you get into a dangerous situation, as you said in the talk, Alice, you will take drastic action. You don't mind denting your car if you're going to stay alive.
That's right, yeah. To choose the least worst situation. Yeah.
And I guess there is some higher level policies, including ethical policies, would also play a role, which one you want to choose.
Quite possibly, yeah.
And so we have a line of activity in our node looking at ethical policies, both with respect to higher level ones and also at the level of sub-symbolic AI. So I guess there could be some opportunities for collaboration.
For sure, yeah.
Very good. Thank you very much. Are there any final remarks or questions before we close this session? If there are no further questions, then thanks again, Alice, for this wonderful talk. We will have another instance of verifiability talk in 2 weeks where Naren Manoj, I hope I remember the name correctly, from Toyota Technological Institute in the US, in California, will talk about security in AI models. And in the meantime, I wish you very happy holidays if you go on Easter holidays next week. Thank you.
Great. Thank you. Bye.
Thank you. Bye.
Bye.